Good morning, all. I am Pooja Piraj, currently working as Assistant Professor in Computer Science and Engineering Department. A very warm welcome to each one of you on behalf of Department Computer Science and Engineering of St. Thomas Institute for Science and Technology, Trivandrum. We would like to thank you all for registering and attending this 3-day national level faculty development program on exploring generative AI models, applications, and innovation, which is organized with collaboration with Tata Consultancy Services.
It gives us immense pleasure to host this program, which aims to provide It gives us immense pleasure to host this program, which aims to provide insights into cutting-edge AI technologies like GAN and GPT models. It focuses on applications in education, healthcare, cybersecurity, and content creations, promoting research, innovations, and ethical understanding of how Gen AI transforms creativity and problem solving. Over the coming days, we will be engaging with expert resource persons, meaningful discussions, hands-on sessions, and collaborative learning. We would like to welcome Mr. Rajiv Srinivas sir, Regional Head, Academic Alliance Group, Kerala GCS, Principal Honorable Dr. A.G. Matthew sir, respected Head of Department Mr. Anup Abraham Matthew, and Ms. Ansi Varghese, HOD in charge AIML. We are delighted to have all FTP resource persons, representatives from management, faculty members, and last but not the least, participants from various institutions. And we hope this FTP serve a productive platform for learning, reflection, and professional growth.
About this FTP, this will be a 3-day FTP from morning 10 a.m. to afternoon 4 p.m. We accept you to all to attend all the sessions. The video recording of the FTP will be provided on YouTube channel and the link will be shared via WhatsApp. During each session, attendance link will be shared. All the participants will be received e-certificates. The procedure of receiving of certificate will be informed at the end of the FTP. We have shared the confirmation mail to all participants till yesterday. Those who didn't receive, they can view it to the coordinators via WhatsApp. Now I would like to welcome Principal of St. Thomas Institute of Science and Technology, Dr. A.G. Matthews, sir, for briefing the sessions. We are honored to introduce Dr. Matthew A.G., Principal of St. Thomas Institute for Science and Technology, Trivandrum, an institute with courses aggregated by National Board of Accreditation (NBA), with an exceptional 28 years of international and multicultural academic experience. Sir has contributed extensively to academic, industrial collaboration, curriculum development, and many. His teaching portfolio covers a wide range of engineering subjects, including mechanical engineering science, design and engineering, engineering wise.
Region Head, Academic Alliance Group, Kerala, at Tata Consultancy Services. With an extensive and diverse career spanning over a decade, he has excelled in roles such as Agile Coach, Technical Lead, Assistant Consultant, MDM Consultant, Corporate Trainer, and Project Manager across leading organizations including TCS, Bed Bath and Beyond, Avantor, and Hubble Incorporated. His expertise covers product information management, data management, workflow management, talent development, leadership, and community outreach. Beyond his corporate achievements, he is a certified mentor, public speaker, keynote speaker, Toastmaster leader, laughter yoga practitioner, and professional, reflecting his multifaceted persona and passion for empowering people. We are honored to have him with us today, and we warmly invite him to share his valuable views and insightful perspectives as part of this FTP. Over to
Thank you.
you, sir.
Thank you so much, ma'am, for this wonderful welcome. I'm really intrigued by the vibrant introduction that you have given. I never thought it would be such elaborate. Thank you so much once again. And it's a real watershed moment for every one of us here who are really keen to enhance their knowledge. The faculty development program, in its first shape itself, is the real need of the hour, where earlier days we used to think, okay, once we have studied, it's just completed, we have to just follow the syllabus. But now we know the real need of the hour is quickly evolve and adapt ourselves. So I believe with the industry academia collaboration, and of course Thomas College, which is pioneering in this, instrumental in these activities, will help us garner through these knowledge sharing sessions and will help our next generation come up with more fruitful results. Thank you so much for having Tejas as the knowledge partner for this academic alliance initiatives, and looking forward for fruitful sessions throughout and have more young generation coming up in limelight with artificial intelligence and so on. Thank you so much and wishing everyone all the best. Over to you.
Thank you, sir, for your valuable insights. Now, I would like to welcome Ms. Ansi Varghese, HOD in charge AIML, to speak a few words.
On behalf of CS department, it gives me immense pleasure to welcome you all as we kickstart this faculty development program on exploring generative AI models, applications, and innovations. The computer science department here at St. Thomas Institute for Science and Technology has always been committed to providing a comprehensive education that prepares students to become leaders. Our department was started in the year 2010 with one batch, and currently we are having two batches for computer science and engineering, one batch for data science, and one batch for AML. Our department has also got NBA accredited last year. Through a rigorous curriculum, we all ensure our students to gain a solid foundation in algorithms, data structures, and cutting-edge technologies like machine learning. However, to teach the future, we must first master it. This FDP has been meticulously planned to provide deep technical knowledge, hands-on insights, and opportunities for academic growth. We are living through a paradigm shift. Until recently, our interactions with the computers was transactional. We gave a command and the machine executed it. Today, with the advent of generative AI, we have moved from machines that merely analyze data to machines that create. Gen AI is not just a tool, it is a collaborator that is redefining the boundaries of software engineering and creativity. This brings the purpose of our gathering, and it is designed to bridge the gap between traditional curriculum and the rapid explosions in AI technology. We are exceptionally privileged to organize this event in collaboration with TCS. This partnership ensures that the insights we gain over the next few days are not just theoretical but deeply rooted in current industry standards and real world applications. I would like to extend a warm welcome to all our distinguished resource persons. We are grateful for your time and expertise. To my fellow faculty members and participants, welcome. Your presence here shows your dedication to continuous learning and academic excellence. I take this moment to sincerely thank our principal for his unwavering support and guidance in making this event a reality. I encourage everyone to make the most of these sessions. Let us explore, innovate, and take these learnings back to a classroom to inspire the next generation of tech leaders. I hope this FDP will inspire you, ignite new ideas, and lead to fruitful collaborations. Thank you, and I wish you all a productive FDP.
Thank you, ma'am, for your valuable insights. Now, on behalf of Computer Science Department, we will formally invite all the resource person, representative of management, faculty members, And last but not the least, participants from various institutions. And we hope this FTP serve as a productive platform for learning, reflection, and professional growth. Now, I would like to introduce our first session for the resource person, Mr. Vivek Paul. Mr. Vivek Paul is currently working as a system engineer, data scientist at TCS Research and Innovation, Kochi, Kerala. With over 3 years of professional experience, he is actively engaged in exploring new and emerging technologies in the domain of responsible AI. He holds a bachelor degree in computer science from IIT, Kottayam. During his academic year, he demonstrated strong leadership and technical skills, serving as an event lead of CodeChef campus chapter at IIT Kottayam. He also gained hands-on experience as a front-end app developer. Mr. Paul is a certified Google Cloud Associate Cloud Engineer, further enhancing his expertise in cloud computing and scalable data solution. With his background in data science, AI research, and cloud technology, Sir brings a blend of academic excellence and industry's innovation to his professional and research. Today, he will be handling Introduction to Gen AI concepts and evaluations.
Thank you,
Over
Pooja,
to you, sir.
thank you, Pooja, for that wonderful introduction. I think you covered everything there. I think I'll start with presenting my slide deck now. Please do tell me once that's visible, and then we'll start with the session.
Yes, sir. Slides are visible.
Great. So yes, the topic for that we have for today is Introduction to Generative AI, its concepts, how it works, and the evolution of generative AI models. And first, we start with the evolution of the language models. So in general, before we go into generative AI, let's just first give a intro on what is AI in itself. So AI is the ability for the computer systems to perform tasks that humans can perform with their intelligence. So it can be speech recognition, language translation, visual perception. These things are very easy for human beings to do, but it can be more tricky for computers to do. And that is where artificial intelligence comes in. So AI is the science and engineering of making intelligent machines, and especially intelligent computer programs. That's stated by John McCarthy. It's an American politician. So the goal of artificial intelligence is to understand and replicate the aspects of human intelligence, human-like intelligence in normal computers. So and then we have from the normal artificial intelligence, we go into language AI. So something that we take up very easily, or we pick up very intuitively, is the normal language. Even babies from a very young age start to pick up words, and they start to form sentences as they become toddlers. And as they grow older, they can handle language very easily. But it is not so easy for computers to do so. So that is where there is a subfield of artificial intelligence which focuses on understanding, processing, and generating human language. And this is very closely related to a field in computer science called natural language processing. And these includes technologies that go beyond large language models. We also have something called retrieval systems, that retrieval augmented generation, which enhances the power of large language models. Now, large language models are one of the central technologies when it comes to language AI, but that is not the only technology that is there. And before we go into that, we'll go into the history of language AI. So this is the sort of the models that came up throughout the years. So initially we had, when it came to natural language processing and all, we had things like bag of words, word to vector, and attention mechanism that came up in 2017. So in 2012, we had bag of words kind of technology, but afterwards, word to vector came. We'll be seeing how many of these work. And then attention mechanism came in 2017. This was a watershed moment, because once attention mechanism came, it gave rise to the variety of the large language models, both generative models and representative models. So here we can see BERT, Distilbert, Roberta. These are all representation models which are used for various representing language in ways. So it can be used for classification tasks or named and entity recognition tasks. We'll be seeing those also. Then we have encoder. These are encoder only models, we call that, or representative models. Then we have decoder only models. These are the GPT models, GPT-2, GPT-3, GPT-4, ChatGPT. All those are decoder only models. These are focused on generative text. These are also called generative models. They can generate text. So that is the two main types of models. And we also have encoder decoder models like T5, switch, and flan T5. So we can see how throughout the years these models have been evolving as new ideas or new technologies have come into picture. These more powerful models are evolving, and as we go across time, the number of parameters of each of these models are also increasing, which makes them more powerful. Now, why is language so challenging for AI? So usually in artificial intelligence or computer science, most programs work with structured data. Data will be in a very structured format. If it's normal artificial intelligence, if you know any sort of classification tasks, then we'll have our records in a very structured format. There will be a certain number of features, and based on those features, the model will be deciding on whether that if it's a classification task, on which class that record belongs to. So an example can be there is a loan application. So the various features of the loan application can be the amount of the loan that is loan amount that is asked for that particular loan, then the loan amount term, how much time the loan is being asked for, then what is the credit score of that person, and so on. So these are the features of the record. Based on that, a model will be looking at the structured data and predicting whether to give that loan or not. So this is a very straightforward way of doing it. There are many models which can do this particular thing. It could be a simple models like random forest, decision tree. Many kinds of simple models can do this particular thing. That's because it's structured data. But when it comes to language, text is very unstructured. There is no structure to it. There is no particular features per se. These are all just collections of words. And when converted to binary into zeros and ones, the language completely loses meaning. So to process language effectively, it must be represented in a structured format. And that is one of the most important challenges that was there in the history of in the history of language AI. Now we are able to process it nowadays. So through language AI, we'll be able to create through embeddings that we put on the language. We are able to create text output, and we can also do other representative model tasks like classifications and named entity recognition and so on. So, if there are any questions, please feel free to ask. Stop me at any time. Is there any questions that has come up till now? I think Sridevi has raised the hand. Any question? Okay, I don't think there's a question. Pooja, everyone be able to ask questions, right? Unmute and ask, or will that be a they'll be chatting the questions? Okay.
Sir, not audible.
Okay. Am I audible now?
Yes.
Okay. You're able to hear till now, right?
Yes.
Great. So feel free to ask any questions in between. So yes, now it comes to representing the language as a bag of words. So this is one of the, if we saw the evolution of the language models, we had seen how bag of words was one of the first thing that came up in 2000. So bag of words is used to represent this unstructured text in a very numerical format. So the text which is there in words and phrases is converted into numerical representation. So first step is tokenization. Then after tokenization, a vocabulary is created for creating this bag of words, in which each sentence is represented using a vector that shows the frequency of each word. And one of the issues is that through this whole process, we are ignoring the grammar, the word order. We only focus on how many times a particular word is occurring. So to give an example, we have two inputs. This is a cute dog and my cat is cute. Now, when we are implementing the bag of words, we'll be first tokenizing it. Now, tokenizing works by splitting these both sentences using the white space. Okay, so when you're split by the white space, this is a cute dog, my cat is cute. Each of these words become a single token each when you split it like that. Now we have the tokenized sentences. This entire thing we have. Now is our thing to create a vocabulary. Vocabulary is what are the words that we know when we are creating this bag of words. So what are the total unique number of words? See, is happening twice, right? And cute is also coming twice. So we'll just take the unique words that are represented here. That creates our vocabulary. So this is a cute dog, my, and cat. These are the tokens that are words that create the vocabulary for our bag of words. And how many words we have in this vocabulary is what shows us the vocabulary size. Okay. Now we come to how do we represent a particular sentence using the bag of words method. So if we take this sentence, my cat is cute, that is our input, right? Then we do the tokenization. My cat is cute. So the four tokens are created by splitting the input using the white space. Now we take our vocabulary and we see how many times each word is coming up in this bag of words. So this vocabulary is basically a bag of words. In this, which all words are being shown or represented in this particular sentence and how many times. That frequency is also represented. That is not there in the sentence. Is there and it comes once. A is not there, so it's 0. Cute is there once, so that is represented by 1. Dog is not there, it's 0. My is there 1 and cat 1. So here we have 0, 1, 0, 1, 0, 1, 1. So this is a vector representation of this particular sentence. Similarly, we can also, whichever sentence that we have, we can create a bag of words representation or a vector representation like this. This is one of the initial ways of representing language. But as you can see, this only sees how many times a particular word is coming up in a particular sentence. It's just frequency representation. This doesn't know which order these words come in. There is no representation of that. What is the meaning of each word? There is no idea when it comes to bag of words. But initially, this is how bag of words in natural language processing, how it used to be represented was using this bag of words technique. Any questions? Is there any questions still now? Okay, I don't think there are any questions. Chats? No. Okay, I'll go forward. So we need to have better representation. So we have seen many problems that was there before. We didn't know what is the meaning of those words. It was just a frequency representation when it came to bag of words. Now we need a better representation for these language. That is where in 2013, a technique called word to vector came in. This was a huge new growth in this language AI because it created a numerical form of representing words called embeddings. Now, embeddings can capture the semantic relationship between words. What do you mean by that? They can understand the meaning of the words and relationship between different words. So how was this word to vector trained? It was trained on large data sets like the Wikipedia data set. So there is a huge amount of data that is there in Wikipedia. So it was used to train this particular word to vector model. And it uses neural networks in which each of these nodes have various weights as model parameters, and throughout the course of training this model, these weights are updated. Now, every word in our vocabulary, here also we have vocabulary, the amount of words or amount of tokens that is there in our original data set, that shows us the vocabulary for this particular model. So every word starts with a random vector. That is our initial embeddings. And during the training, the model predicts whether two words are likely to appear near each other in a sentence. Now, when two words are appearing near each other, when there are, so based on that, these weights are being updated. And if two words have similar neighbors, then that means those words will have similar meanings and their embeddings will be closer to each other. So in this way, this word to vector is able to represent meaningful relationship between words. So we'll understand that in a very pictorial format, so that'll be easy to understand. So here we are able to capture the meaning of words. So if we have something called cat and cube, then we have two embeddings, and these are the vector representations of these two words as per word to word. And are these two words neighbors? So usually when we give sentences, when with cat, usually we have the word cute also associated with this, because cats tend to be cute. So the model prediction is 0.74. So yes, these two words usually tend to be close to each other. So using this training method, whether two words tend to be close to each other, for each word in the vocabulary, like cats, puppies, houses, apple, baby, everything will have a vector representation, which is having a particular dimension, right? So this is for each word having a vector representation. So this is like so things like baby might have. So each of these vectors will have a certain size. So that is something we call as dimensions. And each of those dimension or each value that is represented here can be representing something called a property. So the first value can be for animal. Is that particular word an animal? So for cats, it is 0.91. It is in the range of -1 to 1. So in the cat, it is having 0.91. That is a very high value. So yes, cat is an animal, so that is having a high value. Puppy, it's also an animal, so it is having 0.93, a high value. But houses is not an animal, so it is having a negative value, -0.56. Apple is not an animal, -0.67. Baby is not an animal, but it is having it's a 0.1. It's not a negative value, but we are giving a kind of a close to zero kind of value there. See, so it's like that that we give. Then something like plural. So is it telling about more than one object? So cats, it is plural. So it is having a 0.94 positive value, high value. Puppy, it's talking about a single instance. So it is having negative 0.82. Houses, because it's a plural word, it is having 0.94. Apple, because single, it is having a negative value. Baby, single, it is having a negative value. So like that, each of the dimensions of a particular vector can represent a particular property. So through that, all the words in the vocabulary of our training data will have a particular vector representation. So that is what word to vec model does. Okay. Now these property might not be directly humanly readable. So this is not how exactly the properties might not exactly mean animal, newborn, human, or like that. It is for our understanding that we have given it like this. But what matters at the end of the day is the computer is able to learn the relationship between the words by looking at these properties that is there for each that is there in each of these vectors. Now, coming to the representation of these various vectors. So when we represent these vectors in a 2D format, what we tend to find is that, see, all the animals, cat, dog, and puppy, tend to cluster together. See, that is the vector, the semantic meaning is bringing those words closer together. Building and houses, they are also very close to each other. Apple and banana, which are fruits, are separate and very close to each other. And baby and adult, which are human beings, are also separate and very close to each other. So this is something that we also see in word to vector. Through this vector representation, we are able to capture the meaning of the words. This was not there in bag of words. Bag of words was just sentences and what is the frequency of those words. It did not have any of this. But coming to that was there in 2000 and 2013, we're able to see that the meaning of the words are able to be captured using the word to vector technique. Any questions? Uh, Feel free to unmute and ask. If not, you can chat your question also. Okay, I don't see any questions yet. So we'll go to the next one. Now we have issue. So here we see each word has a particular vector representation, and that is it. But there is an issue there. See, the word bank. There are two kinds of bank. It could be a financial bank where you have an account and you put your money there. It's put there for safekeeping. That is one type of bank. And also we have something called the bank of a river, right? When there is a river like this, the land on the side of it is called the bank of a river. So if the word bank is there and there is a vector representation for it, which one do we mean? Is it the financial bank or is it the bank of a river? That is something that is not there in a normal word to vec, but this is very important in language, right? If I'm saying I'm going to the bank to put some money, then you know that I'm talking about the financial bank. But I was relaxing by the bank of Periyar. If I'm saying like that, you know, like on the side of Periyar, maybe there was a restaurant and I'm relaxing by that. So you know what mean by us being humans, we are able to recognize which bank it is by using contextual clues when we are giving a particular sentence. But a computer is not able to do it. So we need to find ways in which we can help the computer understand this particular difference by using contextual information. So that is where recurrent neural networks comes in. So in the recurrent neural networks, here also we use the word to vector or vector representation for each words. So here also, so we have the issue that word to vec for a word like bank, it has the same vector regardless of which context it is. So words with multiple meanings create issues for the computer to understand, and because there is no contextual information. Now, recurrent neural networks have the way of handling these handling sequences of information and also understand the context in which a particular word is being used in a particular sentence. Now, there are two main tasks that the LLM does. There is an encoding phase for a large language model, or encoding phase for a recurrent neural network, and a decoder phase. And so it also works in an auto-regressive way. So in this particular example, what we are doing, the RNN network is trained to do is to do a language translation. So I love llamas is something that is there in English. So the RNN model is trained to do something called language translation, in which the English is translated to Dutch. So ik hou van llamas is the Dutch translation of I love llamas. So how that works is, it works in an auto-regressive processing. So in the first step, when the I love llamas is being given to the RNN model, it will be predicting the output, that is ik. For I, the output is ik. That is generated in the first step. Now in the second step, this ik is added to our context. So I love llamas ik. Then what is the next word in that should come? So that is where in the second step, how is created by the RNN model. Then again, how is added to the context again. And in step 3, I love llamas ik how. Then what is the next word? Van is being generated. And then van is also added to the context. I love llamas ik how van. And then llamas. That is the entire Dutch translation for I love llamas is created in 4 steps. So this is something called auto-regressive processing. So that we can all see even in large language models, where a particular word is being generated and it is added to the original context in the next step to create the next word. So even if you are using auto-regressive processing is even there in our modern GPT models. Like if you are using ChatGPT, typing a particular prompt, and you are clicking send, you see one word by word that is coming up there, right? It is not the entire word that is text is generated and it just pops up, right? Usually in ChatGPT, the word just comes one by one. So there is this auto-regressive processing that is happening. This is the step that is happening there, but it's happening very, very fast. But you can see those words coming up one by one. So that is an auto-regressive processing. Now, coming to the encoding step. So initially, the process starts with the word embeddings itself. So that we are seeing in word to vector. So I will have a word to vector embedding. Love will have another embedding. Llamas will have another embedding. Now, inputs words are taken sequentially to build the context embedding. So all these general words are taken one by one in the order of processing, and it is added to a context embedding. So this is where the context is identified or context is being represented by the RNN model. And the decoder takes in the context embedding and sees what is the next word that can be generated. So this entire context, it's not just the word that is being used in RNN, because all these words are sequentially processed and the context is being created, it is able to generate the next word, ick. Then once this ick is also added to the original word embeddings, the new context is updated and the next word is generated by the decoder and so on. So we can see how the processing happens, and one by one, the language translation happens in a recurrent neural network. So that is the encoder-decoder architecture of a recurrent neural network. Now we go into something that is beyond RNNs. The next thing is representation models. These are encoder-only models. So here, what they want to do is to represent language rather than generate new text. It wants to understand or represent that language in many ways. So an example is something called BERT. BERT is an example for a large language model, which is trained on a large data set, and it's also a representation model. So we can fine-tune this model for various downstream tasks. So it can be something like classification. So if it's a let's say we have a particular email. Now we want to classify that as to whether that particular mail is spam or not. Is it spam mail or is it a mail that is actually useful? For that classification task also, we can use the BERT model. Or it could be a named entity recognition. So given a text, where are persons being represented there? What are institutions? Or where are the verbs? Where are the pronouns? All of these are named entities, and these can be represented or identified using a BERT model. So these are, after fine-tuning, we can do these. Or paraphrase identification. So to create paraphrases for the various texts, we can also use BERT model. So these are fine-tuned. We have a general representation model, and we can fine-tune it for various downstream tasks. But this is encoder-only models. But what we are concerned about is generative models, or models which can create new data. So generative models is decoder-only models, and this is where new text or new words are being generated. So we have, let's say we have an input sentence like I love. Then what can be the next word that is coming up? That is what the generative models are concerned about. So we have various decoder layers, and after decoder layers, we have a self-attention layer and a feed-forward neural network, which finally results in the next word being predicted. So after I love, what can be the next word that is predicted? But according to this model, it is the word llamas. So I love llamas will be the entire sentence that is being created. There is an example of a generative model, but how exactly this generative model works, we'll be seeing in the upcoming slides. Any questions till now? Is there any questions? Okay, no questions. All right. Feel free to ask questions in the chat as well. I don't see any till now. So we'll go back to the slides. So the evolution of large language models. So here we have generative decoder-only models. So as we had seen, generative models are decoder-only models, and the large ones, especially the ones that have a large number of parameters, are called large language models. So as you can see, as time has gone on, The initial GPT-1 model had 117 million parameters. GPT-2 had 1.5 billion parameters, and GPT-3 has ballooned to 175 billion parameters. Now, nowadays, it'll be even huge numbers of parameters as the large language models are evolving. Now, the LLMs can also include encoder-only models like representation models, but generative LLMs work in the decoder-only uh, mode most of the times, and it is a sequence-to-sequence machine. So, user query is a particular sequence of words or sequence of tokens that we are given, and based on those tokens, based on the query, the generative LLM is able to create its output. It is also called completion, and it will be the completion of this particular user prompt. So tell me something about llamas. If that is the prompt that we are giving, then the generative LLM will be creating these tokens one by one. Llamas are domesticated South American camelids, widely used as pack animals by Andean cultures, and so on. So this is a completion or text that is generated given a particular user prompt. Now we can fine tune the model to follow particular instructions, and we can also create chatbots and a lot of things which can help these generative AI models to answer questions instead of just completing text. So when we are using ChatGPT, it is fine-tuned models that are instruction fine-tuned models that will help give better answers rather than just completion models that we see here. And at the end of the day, what all these models are doing is predicting the next token or what is the next word. It is just predicting, and then as we had seen, auto-regressive processing. One by one, it is generating the next token and then the next token and so on until it creates a completion like this, the entire completion like this. That is how a generative AI model works. Now, coming to something called, so we'll be going to the details of how this generative AI works. So first thing that we have is something called the context window. So what are the tokens, the context of tokens that the LLM will be looking at a particular time to generate the next token or to create the completion, right? So the larger the context window for a particular model, the more tokens it can look at, the more context it can look at for generating the completion. Now, because these models are auto-regressive, like whatever output new token is being generated by the model, it is going to be added to the context for creating the next token. So this the number of tokens will grow as the generated text completion or the tokens that are generated by the model goes on. The context will also grow, but there is a set context window or maximum context length that is available for all models. Now, the input will be something like each of these tokens will be generated. So tell me something about llamas, full stop. That are the prompts. From the prompt, the tokens are generated, and that is what we are seeing here. 6 tokens are generated for the prompt. And then the previously generated tokens, llamas are. Those are also a part of the context itself. This entire context goes into the generative model, and the maximum context length for this generative AI model is 512. We have only 8 till now. So this is going in, and the next word, domesticated, llamas are domesticated, is coming up, and it updates the input. Now for the next iteration, next step of the auto-regressive process, this entire thing, including the prompt, tell me something about llamas, full stop, llamas are domesticated, will go in, and the next token will be generated. That is how the models work, and that is what a context window is for a large language model. Any questions? Okay, no questions till now. Great. So yes, either you're completely understanding it or you're not understanding anything. So anyway, let's go on. Please feel free to ask any questions. So next, we are going to the next idea of tokens and embeddings in generative AI. So tokens and embeddings. We had seen tokens before, tokenization. So that is, these are 2 central concepts that are related to large language models. So tokens are, we have a given sentence input that is going into the large language model. The first thing that the large language model does is to split it into smaller pieces or smaller words or something called tokens. Now, in this case, have the words who preceded. Each of these words are being split into tokens. So have is a single token, the is a single token, bards who preceded. Each is a single token here. Now, it is not necessary that a token will be a complete word. It could be a part of the word as well. So we'll be seeing that in the upcoming slides. So it all depends on what the tokenization model is trained on and what are the priorities of the large language model developers as to what kind of tokenization is being done. And each of the tokens will have a particular embedding that we have seen in word to vector also. An embedding will be there for each of the tokens, and these embeddings will be learned by the large language models in the process of them being trained on vast amounts of data. So in these vast amounts of data will be all split into tokens, and through the learning process, the embeddings will be created, which captures the meaning of each of these words. So every word that is there in the vocabulary for this tokenizer will have their particular embeddings. So when the inputters have the parts of preceded, the tokens will be first generated, and the embeddings for each word that is learned by the large language model can also be generated from these tokens. Now, LLM tokenization. So something like GPT that we use all the time. Let's see if there are any questions before moving forward. No questions. Yes. So LLM tokenization, like the GPT models, have the parts who preceded me left any theme unsung. So there's a question that is being asked or a prompt that is being given to the GPT model. Here we see what are the tokens that are being generated from this particular prompt. So have is a single token, the single token, bard, though it is a single word, it is being split into two different tokens. So that is based on the tokenizer that is used for the GPT models. Then who is a single token? Preceded is a single token. Me, left, any, theme, that is also single token. Then unsung, that is, though it is a single word, it is being split into two different tokens. That is also based on the training or the tokenizer model that is being used for GPT. And the question mark is also, the question mark that is there, that is also its own separate token or a special character. So the generative LLM takes these tokens one by one and sequentially takes these tokens and it generates the next tokens as a part of its completion. So there is also a token limit that is there if you have used generative AI models. There is also a token limit that is there for when we are using their APIs. So that token limit is also calculated based on the tokenizer that is being used for that particular model. Now, how does the tokenizer break down the text? So there are three factors that is there. So first is the tokenizer methods. So it can be methods like byte pair embed encoding or word piece that are used by various models. And second is design choices. How large do you want the vocabulary size to be, and what all are the various special tokens that you'll be including? So you might say, why not include all the words as the various words or various into the vocabulary? The vocabulary will be very huge, but you don't really need to do that because that is also a complexity. The model will become more complex. It will be more difficult for us for the model to be trained, and the resources that are being used will also be more. So we don't want that. We don't want a very huge vocabulary size. So that is also design choice that is made by the makers or the developers of these large language models as to what you want the vocabulary size to be. So here have, the, and all are have and we are different tokens, but bards, that is split into two tokens. B is a different token and ARDS is a different token. Who is a single word and a single token. So we have the token IDs for each of these words. So those are numerical values that represent the particular word in the vocabulary. And the training the tokenizer is trained on the huge data set. And for each word, the embedding will also be created. So what goes into the language model will be these token IDs, right? Have as a unique value. 6975 is the unique token ID for have. Thus, unique token ID is 278, and so on. So these token IDs go into the language model, and the output token ID comes up. And this token ID is looked up uh, in the token IDs list to find out the corresponding token for the token ID, and will be OR. So have the bars who, then OR will be the next token that is being generated by the language model. There is a tokenizer is one of the parts of the language model, and this is how tokenizer works. Let's see for any questions. No questions yet. So yes, let's move forward. Now, the tokenizer can differ based on various factors. It can be the tokenization method. It can be the initialization parameters. What are the vocabulary size that we want? How many special tokens do we want? And also the data set that these models are trained on. So we can compare like various tokenizers that are available to see how their behavior is, how do they perform. We can also see if new tokenizers have improved their model efficiency and accuracy. You'll be seeing that in the coming slides. And there are also specialized model like code generation models will have their own specialized tokenizer, because in a code, how the tokens need to be generated is different from a normal text, right? And tokenizer can vary behavior based on capitalization that is being used in the text, non-English language characters, emojis, code, numbers, special tokens. All of these can affect the behavior of the tokenizer. And there are also special tokens that indicate the start of the text, end of the text, etc. for the model. So all of these are parts of the tokenizer. Now, let's say we have an input text, like this is a string input, English and capitalization, which is in all caps. There is a special character, the music symbol, and a Chinese special characters. And there is some code as well, and a mathematical equation. So these are text that is there. Now let us see how different tokenizers tokenize this particular given text. So the BERT-based uncased model that was released in 2018, it has this BERT-piece tokenizer, and the vocabulary size is 30,522 tokens. So around 31,000 tokens this particular model has. And also special tokens like unknown token for words that are not in this vocabulary. There is only 30,522 tokens that are there. These are the only words that the model understands. So if there is some token that is coming up that is not there in the vocabulary, it will be represented by the unknown token. There is a separator token. There are padding tokens used to fill unused positions in the model's input context if the model is expecting a particular size of context. And then classification token is used for text classification. Masking token is also used for certain tokens if that model has to predict that particular token, right? So in the tokenized text, so these are original text. In the uncased model, the capitalization is not looked at all. So English, though it starts with capital E, that is ignored. So it starts with small e, and is a different word. Capital is a different word. Ization is a different word. So this double hashtag represents that it is a continuation of the preceding token. So though these are two different tokens, we see that these are continuation. So capital is a different token and ization is a different token. Then we have two different, the music symbol and the Chinese symbol. These are not a part of the tokens vocabulary. So those are represented by the unknown tokens, U and K. Those special tokens are used to represent those. Then show, underscore, token, all these tokens. So token is a different one, and token, because it's a plural, it is having the double hashtag to represent that this is a single word, but these are two different tokens. That is how this tokenizer handles this text. So we can see that the tokens are generated like this. Now we see another model, and we see another tokenizer, and we see how that tokenizer represents the same text. So here the BERT-based model cased. So this is also released in 2018 itself. It also is very similar, but the only difference here is that this model is a cased model. It also looks at the capitalization of these words. So here we see English. The E is capital here. So English is a single token and is a single token. But when it comes to the word capitalization, so this one, it's all caps. So previously it was seen in the uncase model as capital and ization. It was two different words, two different tokens. But here it is split into a bunch of different tokens. CA, PI, TA, LI, Z, AT, ION. So this is how the word-based cased model treats that particular word. It splits into a huge number of tokens, and each is shown with a double hashtag to show that it is a continuation of the preceding token. And here also, the music and Chinese characters are unknown because it is not a part of the tokens or the model's vocabulary. And here also we see that there are differences in the way in which each of these tokens are being learned, and the tokens that are available for this word-based model, and the way in which the tokenization is done is also different between different models. Now, when it comes to GPT-2, it's a different kind of tokenization method, byte-pair encoding. And here we see that the number of vocabulary size has also increased. From around 30,000, it has increased to 50,000. And there is also a special token end of text that indicates the end of text generation. So here we see that English and capitalization is also split into various tokens. And there is a bunch of unknown tokens here. And after that, it also has the show tokens. Everything is being split into in a different way by the GPT-2 tokenizer. So that is how GPT-2 tokenizer works. And now, as GPT-4 works, here we can see here also byte pair encoding is used. But as time goes on, we see the vocabulary size is also increasing. The more computation power we are able to put into it, so we're able to have more tokens. More than 1 lakh tokens are there for the GPT-4 tokenizer. Here also end of text is a special token that is there. So here English and capitalization. So capitalization are split into two. So these are two separate tokens. And here also the elif, which was separate tokens before, is now, because there is a more number of tokens here, it is a single token. So that means it will be able to do programming better, because such tokens are also a part of its vocabulary. And the equation is also represented like so. So as time goes on, the tokenizer is also able to better capture the tokens, or better able to handle it by having a larger vocabulary size, because more computational resources are available. So let's see if there are any questions. No questions yet. So feel free to ask any questions in the chat, and you can also unmute yourself and ask questions. So please feel free. Okay, we'll continue. So language models holds the embeddings for its vocabulary. So we had seen that the trained tokenizer has a particular token ID for each token. And for each token ID, there will be a corresponding token. Now, for each token ID, there will be a corresponding embedding as well. So the tokens need their embeddings. What does embedding do? Capture the meaning of that particular word. So through the language models training process, these embeddings are generated for each token ID or each token. A particular meaning embedding is being learned by the language model. So before the training, the embeddings will be randomly initialized for each of these tokens. And through the training process, the language model will be trained on a huge amount of data. Data that is there in the internet, text that is there in the internet, Wikipedia data. A huge amount of data will be put into the language model, and we'll see which are the words that are coming closer to each other, and which are the words neighbors, which are the words which have similar meanings, and those similar meaning words will have similar embeddings, and the words which are different will have further apart embeddings. So these are all happening as a part of the model's training process. And after that is completed, each of the words in the token's vocabulary will have its own corresponding embeddings, which represent the meaning of that particular word. So that is what the language model does. Then once this word embeddings are created for the language model, what it can additionally do is impart additional context on top of the word embeddings. So the have the bars who preceded, if that is be the input that is coming up, each of the words will have additional embeddings or additional processing that is being done by the model to impart more contextual data into these embeddings. So contextualized token embedding vectors are being created. So how does the contextual data is added to the uh, into the vectors? That we'll be seeing. It is through mechanisms called self-attention, multi-head attention. How that works, we'll be seeing. So it is basically seeing the relationship between different words that are appearing in a particular sentence. So we'll be seeing how that works. So at the end of the day, language model, what it does is it takes the embeddings, it takes the tokens, it looks up at the embeddings for those each of these words, and the language model is able to look at the entire context and add contextualized information into these vectors for each word. That creates the contextualized token embedding vectors for each word. So that is something that the language model does. So this is even more useful, even more contextualized, even if the same word like bank has different meanings, because the context is also taken into account by the language model. After the contextualized token embedding is there, we'll be able to understand, or the language model will be able to understand whether this bank refers to the bank of a river or a financial institution, the bank that we go put our money into. So that is something that language models are able to do, which previously the word to vector and all were not able to do. So here, so this is basically what it does. Tokenization, have the bars who preceded me, left, any, theme, and sum. So here, if this is the input, it splits it into tokens, have the bars who preceded, and then the token embedding vectors are initially learned by the language model, which captures the meaning of each of these tokens. So the token embeddings are first created. These token embeddings go into the language model. It looks at everything. It understands the contextual information, and it adds the contextual information into these token embeddings, creating contextual token embedding vectors that comes out of the language model, which incorporates additional contextual information into these embeddings, which helps further understand language for the model. So let's go into the working of large language model. How exactly does this adding of contextual information works? Any questions? No. Okay. So we'll be going to more detail of how large language model works. It'll be a bit more technical here. So let's go into it. So now coming to the overview of transformer models. So it was initially introduced in 2017. It is using a paper called Attention is All You Need paper. So that is where the self-attention and how transformer large language models can be created from using that technique was created. So what it initially does at a high level view is that we give a particular prompt, write an email apologizing to Sarah for tragic gardening mishap and explain how it happened. When it goes into the transformer large language model, the generation that is created or completion that is created will be Dear Sarah. So it is creating this particular email. Dear Sarah, I'm writing to apologize for the incident last week and so on. So a generation or the email will be created based on the prompt. Now, how can this work? So here also, as we had seen, the auto-regressive method is being used. So the prompt, write an email apologizing to Sarah for the tragic gardening mishap, explain how it happened. When it goes into the transformer large language model, one by one, the tokens will be created. Dear will be created. That will be added to the original prompt, and the next token is predicted. Dear Sarah. Then it will also be added. Dear Sarah will be there, and the next token, that is comma, is created. Then the new line to do the enter will be created, and so on. The entire email will be generated like this. So that is how the token by token generation is happening in the transformer based large language model. And each token, when it's being generated, that constitutes a forward pass through the neural network of the large language model. So after the first forward pass, the dear token will be generated and will be added. And second forward pass, Sarah will be created. And then forward pass, comma will be created. Next forward pass, new line will be created, and so on. So that is how the sequential process of creating the LLM generation works in the transformer large language model. Now, coming to the components of this forward pass, how does that work? So there are the main components of a transformer large language model are, firstly, we had seen the tokenizer. We had seen how that works. There is a vocabulary, corresponding token ID, and it can create the embeddings as well. So then there is a stack of transformer blocks. So transform block 1 and so on. So we have n number of transformer blocks. So initially in the paper there were 6 transformer blocks, but nowadays in most modern models there are more than like 100 transformer blocks will be there. What is there in each transformer block? We'll be seeing it. Then at the end we also have a language model head. This language model head is finally what gives out or spits out the next token that is to be predicted. So any questions till now? No questions. Okay. Okay. Fine. So we'll go to the next part of it. So what does the language model head do? It takes the output probability of this entire transformer block stack and it spits out the probability score. It looks at the probability score and based on that it selects the next token that is to be generated. In this case, it generates this deer. So the tokenizer, the tokenizer vocabulary and the token embeddings. So coming first is the tokenizer itself. We have seen before for the vocabulary that is there. If there is 50,000 words that are there in the vocabulary, there will be a corresponding token ID for each of them, and the model itself will have the token embeddings for each of the token IDs. So each token will have its own embedding that is learned by the large language model. So that is what the tokenizer does. Then we go from the tokenizer, we'll be coming to the transform block. Before we go there, we'll go into the language model head. So it goes in this format only. It goes from tokenizer, it goes into the stack of the transformer blocks. And finally, the output of these transformer blocks goes into the language model head. So for each of the generated token, it goes through all the transformer blocks. And after passing through this entire stack of transformer blocks, the output goes into the language model head. So what it produces is the probability distribution for the next token. What is the next token that should be predicted? That is created or understood by the language model. So this process repeats one by one. So after then one token is predicted, it goes into the back of the prompt, it is added to the context, and the next token is predicted through it going through this entire stack once again. But what is the next token to be predicted? That is decided by this language model head. Now, how does it do that? That is where the token probability comes in. So the language model head sees this probability distribution that comes from the transformer block as to what is the most probable next token to be predicted. So we have seen that the prompt is to write an email. So the first token that comes after that is usually dear, like dear Sarah or dear Thomas, whatever. So dear is usually the next token that should be predicted here. So from there, dear is having the highest probability distribution, and the other tokens, every token will have a distribution, but other tokens will have very few. For example, the exclamation point is having a very small probability value, and the last token with different word is also having a very low value, but dear is having the highest probability. So this probability distribution is created by the language model head, and usually the most probable word is being is selected, and that will be the next token that is predicted. So there are various ways. So various ways of choosing the token. So there is that is a decoding strategy that is used by the language model head. So the simplest strategy that can be used by the language model head is the greedy strategy. So given the list of tokens, we see output token probability, which token is having the highest probability. Here, deer is having the highest probability, which is 40%. That can just be given out. So that could be a decoding strategy, the greedy strategy. Or a better approach can be something called sampling. So here we see that deer title and to everything has a particular probability percentage that is assigned to it. So in sampling, it picks from the list of tokens, but the chance that a particular token will be picked will be based on the probability, the probability value that is assigned to it. So if it's sampling, then deer will have 40% chance of being picked, and title will have 13% chance, two will have 8% chance. So the email can either start with two, two Sarah or something, or it can also, there is a bigger chance that deer will be selected. So dear Sarah, and the email will be created. So that is the sampling strategy. So there are various strategies for the language model head to select a token as well. So if we are using sampling, this will be more natural. Instead of just always going for the highest probability token, we'll also have a better varied result uh, when we are using a sampling strategy. Any questions here as far as the language model head is concerned? No questions. Okay. If there are any questions, any doubts, please feel free to ask. Unmute yourself and ask. Okay. Next, the advantage is that advantage of this transformer-based processing is that transformer allows for parallel computation. So each of these tokens can be processed independently during the text generation process, and the tokenizer first splits the text into the individual tokens, and each of these tokens can follow its own separate computation path and create the final output from the language model head. And for the final token, the next token will be predicted here. So the advantage here is that it helps in scaling for larger context sizes, because no matter how large the context size is, because all the tokens can take its own parallel path through the stack of transformer blocks and through the computation process, the processing of the entire large language model can be much faster compared to the previous methods like RNN, in which you have to go one by one only. There is no parallel processing per se. Here we can have parallel processing for each token, so that can help in scaling it. Now the context length, here also the same as before. We have a context length. There is a limited amount of context that can be taken in by the large language model at a time. So it can be a 4,000 tokens or something like that. But that includes both the prompt and the completion that is generated, or the output that is generated. Both of these will be a part of the context length limit. Now that defines how many, basically context length is how many tokens that can be processed by the large language model at a particular time. And each token will have each token stream will have the input vector, that is the embedding for the particular word, and the positional info, or as to where this particular word or where this particular token is appearing in the particular prompt or in the document. So that positional info will also be a part of the input vector, and the output vector is what comes out of the transform blocks. So here it will have all the information, contextual information that is added into it. So that is the output vector that comes out of the transform blocks. Now, larger the context length, the more amount of context will be, more amount of tokens can be processed by the large language model at a time, and there will be more parallel streams of processing like this that goes through the language model transform blocks. Okay, and one aspect of speeding up this generation is using key value caching. So we'll be seeing what keys, values, and queries are. So key value caching is also something that is there. Once all these calculations are made for these tokens, these can all be cached. All these calculations can be cached, and the next token can be processed to create the output vector for that particular next embedding. Now, in the key value caching, if we are implementing that, only the latest token stream need to be processed, and the next token can be processed or predicted by the language model. So this can help speed up the text generation. Now, coming to inside the transformer blocks, how that works. So the core processing of the transformer block consists of like multiple blocks. So in the original paper, the number of transformer blocks was around 6. That changed to more than 100 papers or 100 transformer blocks in the newer large language models. So this number of transformer blocks in the stack is increasing as time goes on, and each block processes the input that comes into uh, the transformer block, and it passes the results or resulting embedding vectors into the next transformer block. So it goes in and to the next block, and it also does its processing, creates a new vector embeddings, and it passes it to the next transformer block, and so on. So these stacked blocks help in the deep representation learning. It is able to understand the meaning of the words and relationship between the words to provide the best possible contextual information. So how that happens, we'll be seeing. So for each transformer block, let's now go into what the transformer block does. So each transformer block has two parts to it. One is a self-attention part. Second is the feed-forward neural network part. So first is the attention layer or self-attention part. That is attention layer. What it does is it looks at it integrates the relevant information from other tokens and the position of this particular word into the embeddings for that particular token. And the feed-forward layer, it is a neural network which handles the models processing and gives us the output for that particular transformer block. So let's see how this feed-forward neural network works. So we are now the movie The Shawshank Redemption. So if the input is the Shawshank, then the model should predict the word redemption. Okay. So the feed-forward neural network, after the self-attention, it is able to store the knowledge, store such knowledge during its training process on this large amount of data. It would have come up through similar movie names. It's trained on the entire Wikipedia data, so it might have come through this particular movie name. So such information is being stored in the neural network weights that is there in the feed-forward neural network part of our transformer block. So it is able to identify such patterns, and that information is being stored here. So it's at the end of the day, it helps as the information stored for the next word prediction. Now, it is not just memorizing huge amount of data that happens in this particular large language models. It is not basically a database. It is able to identify patterns, and because it is looking at patterns, it will be able to perform well for unseen inputs as well. Even if it has not seen that particular sequence of words or sequence of tokens in its training data, it will be able to generalize and give the next token prediction based on the patterns that it has identified during the training phase. So that is what LLMs are able to do. So any questions yet? Okay, no questions. Okay, feel free to ask any questions, please. So yes, so now it's coming to the attention layer. So the attention layer here is where the context is being added to the given word embeddings. So it is not just simple memorization is not enough here. You need this attention mechanism which adds the context. So let's say there is an example. The example is the dog chased the square because it. Now, what does this it refer to? Does the it refer to the dog, or does the it refer to the squirrel? We don't know. So we need this contextual information to be added to the it to understand whether it refers to the dog or does it refer to the squirrel. So that is what happens in the self-attention part of our transformer block. So given the token embeddings for a particular word along with the positional information, after the self-attention is done, it is enriched, the output vector is enriched with more contextual information. So the it, whether it refers to the dog or the squirrel all that information will be added to the output vector after the self-attention part of it. So this helps the next word that is being predicted to be very context aware, because all this information is being added through the self-attention layer. Now, the two main steps is so the self-attention itself. The two main steps is the relevance scoring, and all this information is being combined to create a single output vector. So we'll be going to the details of how it does. So one of the things is that even in the attention part of it, it is not a single attention head that works. There will be it's something called multi-head attention that works in transformers. So we have multiple attention heads that works in parallel, and all the output of all the attention heads will be combined together to create our enriched context information for that particular token. So let's see how self-attention works at a very high level. So we have the word, the animal then crossed the street because it was too tired. Okay. So here, the word it, what it is most related to is what self-attention is. At a high level, what does it refer to? So it compares it with all the other words in the given sentence. So the same sentence is repeated twice here. So it compares it to all the other words, and the more related it is, the more higher the color, the darker color it is represented with. So after the self-attention is done, for it mostly refers to the animal. It doesn't refer to the street. The animal didn't cross the street because it was too tired. Now the street cannot be too tired, right? The animal was tired. So it does not refer to this noun, but it refers to this noun. So after self-attention, it is able to have those associations between the words and identify that it refers to the animal, which is showcased with a higher value as opposed to the street. So that is what self-attention is able to do. It is able to understand the relationship between the tokens in these sequences. So now coming to the details of how these self-attention works. So it has three different things. There is a query, there is a key, and there is a value. So this is created by, so once this query, key, and value is there, it all works with vector multiplications on the word embeddings for each word. The query, key, and all are multiplied to create the do the processing for self-attention. So what is the size of these queries and keys? It is represented by the architecture that is used for this particular language model. It is generally smaller than the word embedding. So if the word embeddings for thinking x1 is of 512, the query, key, and all can be of a smaller vector size, like 64 vector size. And so initially what we have is the embeddings, the word embeddings for both the words. Thinking and machines have its own word embeddings. And we have the corresponding queries and keys and values for each one as well, each of these words as well. Now, what does these queries, keys, and values mean? So a query is every word, initially itself, every word is represented by the embedding. That is the normal vector representation, which just captures the meaning of it. So each will have a vector representation. It is an action, and fish will be a vector representing a particular object, because fish is an object. Now, what is the query? Query is what is the word that you're looking for. So if each is the vector that we are having, the query for each will be basically looking at which is the word or which is the object that this each is acting on. What is being eaten? So it can be eating fish. So that is the query that works on it. And key that is there for each word will represent what that particular word means. So fish is fish, and the key for the fish object will have the idea that it is an edible object. So that is what the key will have. And the value will be information, there is more contextual information for that particular word. So the value of the fish will be, the fish is an object that can be eaten. So that will be there the value vector. So each of these query, key, and value are vectors that represent various aspects of a particular word. So for thinking, the query will be regarding like what is the object that is related to this thinking. That meaning will be represented in the query vector. The key vector relates to what that word is. So it will have aspects or attributes of that particular word, and values is the uh, uh, final value vector of that particular word, which has the contextual information also added to it. So fish, if it's eat and fish, then fish will be the object that can be eaten. So that will be the final value vector. So how these vectors are created, or how these are uh, computed in this large language model, we'll be seeing in the next slide. So now we have seen query, key, and value. Now how are these created, or how are these values learned? So when the model is predicting the next sentence, the cat eats fish. If that is the what is expected of a uh, particular model, and if it gives a wrong result, then the error loss, when it's during the training process, it adjusts the weight and weights of the query, key, and value according to the, because the prediction is wrong, the weights are adjusted, and the prediction is right, again the weights are updated as per that during the training process. So through this, the query, key, and value vectors for each token is generated, and once the entire training process is complete, for each token, like whether it be fish, rice, bread, eat, everything will have its own query, key, and values, and the queries will have will learn to see, the queries will be of what this action will be taken on this particular token, and the value will be, it'll be learning to carry the useful information as to a cat can be a subject or an agent in a particular sentence. It can do things to other objects. So all this can be learned in that value vector, and over time will be this model will be able to understand all this and store it through these vector representations. Any questions? Okay, no questions. Feel free to ask, unmute yourself and ask. Okay. So here what we do is, let's see how the computation works. So here we have the thinking machines. So embedding initially for X1 and X2, both have their own word embeddings, and each have their own queries, keys, and values also. Q1, K1, and V1. You have both these values for both these words, right, or both these tokens. Now for each word, the query is multiplied with its own key and all the other keys of all the other words as well. So in this case, we only have two words or two tokens. So the first query for the first word is multiplied with its own key. It gives a high value. And for the next key also, its query is multiplied with the next key. So that is 96, is a lesser value. So if you remember, query is looking for what are the other words that this current word is related to. And key for a particular word carries information as to what its attributes are. What am I? What kind of a word am I? So when we do this vector multiplication, what happens is we are able to identify how related these two words are. Okay. So thinking, when we are multiplying Q1 with K1 itself, we are seeing how related that word is to itself. So we are having a very high value here. Next, this Q1 is multiplied with the K2 for the next word for machines. We are having a 96. It is also kind of related to this thinking machines is related. So it is having a 96. So that is the next score that is being generated. So this dot product is what happens first. So it is done across all the different tokens. This query is multiplied with the keys for every other token. That is the first step. So in this case, only two are there. So that is what is being done. Now, this dimension of the key. So the dimension of key is 64. So the root of 64 is 8. So we are dividing the score by 8. This is a part of the normalization process. So we want to stabilize the gradients during the training process. So that's why we divide this particular score of the dot product by 8. So we get 14 and 12. by after the division by 8. Now for this 14 and 12, it is passed through a softmax layer, and what it does is it turns it into a probability distribution. So all this the all these numbers will be adding up to a total of 1, and all the scores will be positive as well. If there is a negative score that is coming up, after it passes through the softmax layer, will be positive, and all of those will add up to 1. And these normalized scores, 0.88 and 0.12, represent how much weight each token, each token's value will be contributing to the final output. That is what happens here. So this softmax output is multiplied with the corresponding value. So value, as you know, is the how much what that particular word means. That is represented in the value. But how related this particular word is to the other word represents the score. So we are now multiplying that value of that particular word with how much attention should be given to that particular word based on the query and key multiplication. So this is how the attention is given to various words. So once that multiplication is done, it is both added up and the final sum or context aware representation for this word is created, that is Z1. So this is again repeated for the second word as second token as well. And if there are other tokens, for each token, this process will be repeated to create the context aware representation. Right. So the particular score is multiplied with the vector representation for that token, and also for all the other tokens there will be a given score based on the query of this query and its own key. Based on that, there will be a score, and its value is multiplied, and all are added up to create a final resultant vector which has all the contextual information as well. Okay. Similarly, Z1 is our first contextual vector. Z2 is the second contextual vector, like that. So like that, the processing is done. Now we saw for a single word. We are doing it one word at a time. Now to speed this up much faster, we'll have all the various, we use matrix operations. So X will contain all the various word embeddings and will be directly multiplied with its corresponding query vectors to create the queries, keys, and value vectors. And the softmax is put on top of the query into the key transpose. That is a dot product, right? That we had seen earlier on a one-by-one basis. It will be done in a matrix format to speed things up much faster. And we'll be getting the final resultant vector by multiplying this entire thing into the value vector that we had seen earlier. So the final resultant vector we'll be getting in a matrix format. This is a much faster way of doing self-attention. Same thing that we had seen here, we are doing it in a matrix format here. Okay. Now, this is till we had seen here. This is for a single attention head. This is done multiple times using multi-head attention. So the first attention head will have its own queries, its own keys, its own values for attention head 0, and its own query key and value matrices are created. Similarly, second attention head will have its own queries, its own keys, and its own values, and it will have its own weights as well. So if there are 8 attention heads, then each of those 8 attention heads will have its own sets of keys, queries, and values, and each will be looking for a different aspect, let's say. So that is how all these multiple attention head works in parallel, and each of these attention head creates its own resultant vector. So first attention head will have Z1, second attention head will have Z2, third attention head will have Z3, fourth attention head will have Z4, fifth attention head will have Z5, sixth attention head will have Z6, seventh attention head will have Z7, eighth attention head will have Z8, ninth attention head will have Z9, and so on. So this is how the attention heads are created. high value for this absolute positional encoding. But the model then assumes that there must be some relevant positional encoding has to start from here itself. So it is not absolute anymore. So it will help in going beyond such absolute position into something called a relative position. And the rotating vectors keep on rotating in this embedding space, and it helps add this positional information of the tokens as the model is being trained. And where this is added is applied during the attention step in the forward pass of the model. The positional encoding is embeddings is added to the particular token, and it helps understand the context as a whole. So that is where the positional encoding happens for a large language model. Any questions? Okay. Okay. So positional information is also integrated into the before the queries and keys, all those computation happens. The positional encoding is also added into the context to provide better information as to where the tokens comes up in the query, and finally the enriched context that comes up out of the self-attention layer will have the positional data also as a part of it. Now, summary of transformer large language model. It generates a token one at a time, and each new token that is generated will be appended to the original prompt for the next forward pass, that is auto-regressive processing. Three major components of a large language model is a tokenizer, a stack of transform blocks, and a language modeling head. And the tokenization process, the text is broken into tokens, and each of the tokens will have its own embeddings. The forward pass passes through all stages sequentially, and language model head, it takes the probabilities, it scores the probabilities for the next token, and based on this decoding strategy, whether it be greedy strategy or a sampling strategy, it will be predicting what is the next output token to be predicted. So that is a summary of transformer large language models. Now we come to the last part of our session, that is prompt engineering. So how do we control the model's output? So we can adjust the model parameters to have our desired output. So we have parameters like temperature, top P, that controls the model's output. So the LLM assigns a likelihood score for the possible next token. So if the sentence is "I am driving a," then there is a higher probability that this is a car or a truck than an elephant. You might not be driving an elephant, right? So elephant will have a lower likelihood, and tokens like car and truck will have higher likelihood of being selected. Now, which of these tokens get selected? It is we can control that by using temperature and top P. So how that works, we'll be seeing. So temperature, it controls the randomness or creativity in text generation. So if it's low temperature, then it always picks the most likely token. So if car is the most likely token, that will be the one that is being that will be picked. That is controlled by the temperature. Now, high temperature, it allows the less probable tokens to be created. So here we see that the probabilities are more or less more close to each other. So the higher the temperature, there is a more creativity or more randomness that comes to picking the next token. So if it's low temperature, the model's predictions or model's output will be more predictable. But the higher the temperature, the more variability is being put into the model's output. And now top P. Top P is nucleus sampling. So this is also similar to the temperature. So when it's a lower top P, what happens is it sees there are only very few tokens out of the probabilities that can be taken, or there is an option for the model to pick that is reduced when the top P is of a lower value. But when the top P is a higher value, then the model will have more options out of the probability distribution. So when it's low, only car is out is is in the sample set for it to select. But when the top P is a higher value, we are having more tokens from the probability distribution as a in the set for the language model head to select. So here also it works more or less similar to the temperature, but there's another thing that we can control to affect the output of our particular large language model. Now, intro to prompt engineering. So prompt is given by the user to the large language model to get the desired response. It can either be questions, statements, or instructions to the large language model. So we can also use it to evaluate the model output and design certain safety measures. So usually the prompting is an iterative one. We'll give a prompt, we'll see the result, and we'll improve the prompt. And it requires a certain amount of experimentation. And there is no real perfect prompt design. We can always improve the prompt by adding more information and doing certain optimizations. So using these prompt engineering techniques will help us leverage these leverage the large language model capabilities better. So the instruction-based prompting is so there's when the user is giving a particular instruction to the large language model to answer a specific instruction or do a task. So it can be much better than open-ended prompts. We are giving clear instructions. So the instruction can be something like the supervised classification instruction or search instruction. To summarize a text, it can be something to generate some code or named entity recognition, like identify people from a particular text or identify institution from a particular text. All these can be named entity recognition. So these are the various instructions that we can give to a large language model. So a wide variety of applications the large language model can be used by correct prompting. So we have various formats. So for example, in summarization, we have something like instruction will be summarize the following text and we'll be giving the context of the data also along with it. Or we'll be first giving the data and explain the above in 2 or 3 sentences. These are all summarization prompt, and this is a format that we can use for summarization task. Similarly, classification. Here we can see, is the following text neutral or negative? That is an instruction. An output indicator can be the given text and we'll give the data and the sentiment. Is it a positive, negative, or neutral sentiment? Similarly, classification, different classification like this also we can give. We can give output indicators also for the classification prompt. Similarly, named entity recognition, we can give definition as to what is an organization, what is a person, what is a location. We can give definitions. Then we can give exclusion criteria as saying that verbs and adjectives are not entities. And then we can extract, we can give the instruction and give data for it to extract the entities from. So named entity recognition, the format of creating a prompt will look something like this. It will have definition, it will have exclusion criteria, it will have instruction, it will have data. So using all these various kinds of formats, we can give or we can create a variety of prompts. Now, prompting techniques, there are certain things to see. So specificity, we need to clearly and specifically describe what we want the model to generate. We don't want the model to be hallucinating. So we'll ask the model to respond with, I don't know, if they're unsure of it. It can give hallucinated responses, absolutely wrong responses, so we don't want that. So the model does not know a particular piece of information. We want to say, I don't know. And we want to order the instruction either in the beginning or at the end of the prompt. Like the most important instruction should be either at the beginning of it or at the end of it for the prompt to give the best results. Now, the more specific we are, the better the results from the LLM will be. And if we don't give clear instruction, the model will misinterpret what the task is at hand. Now, as the complexity of the prompt increases, the advanced prompt can have more complex formats. It can have the persona, define the role. Like you're an expert in astrophysics, then you can give a particular instruction. So that is a persona that we are giving for the LLM model. Then we'll have the instruction. We can clearly say the instruction and we can specifically mention what is the task that we want the model to do. We can have context, provide background information for it to do the task. We can have format, of the output. What exactly is the output format that we need? Do we need it in JSON? Do we need it in a certain format? We can give that. We can indicate the audience. We can indicate the tone. We can give the data that we know need for the LM to do a particular task. All this can be given as a part of more complex prompts. So all these are, as we can see, the ones we had seen earlier, the persona, instruction, context, format, audience, tone, data. All this can be used, either chosen to be used or not, or excluded based on what is our requirement for a particular large language model task. So we need to experiment with each of these to generate the best possible output from the large language model. And in context learning or providing examples, this is the zero-shot prompting, one-shot prompting, or few-shot prompting, in which we are giving examples. So if it's a the initially, if we are giving a intent classification or the sentiment analysis, there is a negative, neural, negative, positive, or neutral. We are giving a text, and we are just directly telling without any examples as to see what is the sentiment of this particular sentence. One shot will be giving an example. I think the food was all right. It is a neutral sentiment. I think the food was okay. Now we are asking this LLM to give the output. In few shot, we'll be giving a bunch of examples, a negative, positive, and a neutral example we are giving as an example, and then we are asking. So the more examples we are able to give, the more performance that the LLM will be able to give us. So that is a in context learning. And chain prompting is also something that we can do. So if you have a huge task like generating a sales pitch for a new company, then first prompt can be for to create a product name for a particular product given the features. We give to LM and we generate the name, and we use that name to create a product slogan given the features again, and we'll generate a slogan, and then create a sales pitch based on the features, the name, and the slogan. So instead of making the LM do all of this together in one go, we split it up, and it will be able to give a better prompt result. So that is one thing, and we can also do reasoning with prompt. So reasoning can be done with things like chain of thought, in which here we are giving Roger had 5 tennis balls and he buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? So one-shot prompting, we'll just say that the answer is 11. Now, when we give another such word problem, it is not able to do it because it doesn't know how this 11 came up. It just randomly spits out a number here. But chain of thought, we are giving the thought process of 5 plus 2 into 3. 5 plus 6 is equal to 11. We are giving that chain of thought in our reasoning process, in our chain of thought prompt, and then we give the answer. Then, when we are giving the next word problem of cafeteria and the number of apples, it is able to properly do that calculation and give the answer that the answer is 9. So, chain of thought is an ability for the large language model, or one way of prompting to do the reasoning as well. And zero shot also we can do chain of thought by just giving this reasoning step. Let's think step by step. So if we give that particular sentence in the prompt, it will be able to do this particular reasoning as well. That is zero shot chain of thought as well. And self consistency is also something that can be done. So we'll give different temperature and toppy values for the LLM, and we'll give the same prompt multiple times, and we'll do a voting on the answer. So even if one of the answers is wrong, as long as there is a majority of the answers in which the answer is 11, the majority vote will be taken, and this is to make sure that the correct answer is chosen by using the self consistency. By multiple times we are prompting the LLM with different temperature values. So output verification, we can do all these things. We can even see, we can remove profanity, we can remove PI, we can remove bias, and all those by using the output verification. That can be done using the reasoning prompts as well. And we also have constraining and validating output. We have various methods like guardrails, guidance, LMQL. All these are putting the constraints on this output to make sure that it follows certain requirements. So that is also, you can look into things like guardrails to better make sure that the LLM follows a certain requirements that you have. It can be against bias and fairness and all. You can put guardrails on top of it. And prompt engineering summary is that prompt engineering helps in bringing out the creativity and doing more complex tasks using large language models. It can be advanced techniques like in context learning, chain of thought, reasoning, and all. And effective prompts will improve the communication with the LLM, and it will give us better results. And mastering these prompt engineering techniques will help us unlock the power of large language models for better quality responses. With that, that concludes our session for today. Feel free to ask any questions from throughout the session. Otherwise, that's the end of the FTP session. Pooja, over to you. If there are any questions, please feel free to unmute and ask. Otherwise, that's the end of it.
Thank you, sir, for a valuable session. On behalf of the Computer Science Department, I extend my heartfelt gratitude. Your expertise, clarity, and engaging presentation have truly added immense value to this FTP. We deeply appreciate the time and efforts you have dedicated to sharing your knowledge with us. As a gesture of our respect and appreciation, we are honored to present you with the Certificate of Appreciation. Thank you once again for your valuable contributions and for gracing our program with your presence. We look forward to more such inspiring interactions in the future, sir.
Thank you, Asha. Thank you so much.
If anybody have any doubt regarding the session, you can ask now. Nobody is having any doubts? I suppose nobody is having doubts.
Okay.
Okay, thank you, sir, for the valuable session.
Thank you.
Look
Thank you all.
forward
Thank
for
you, Asha.
meeting you again.